go to the next presentation. I think it's from Bruce Mellado. Bruce, if you can please put up your slides and start.
Can you hear me?
Yes, we can hear you.
All right. Trying to share.
Okay. Yes, your slides are up.
Excellent. All right. So I will dive into it. We're going to be dealing with a concrete question of the impact of non-pharmaceutical interventions, and we'll end up with a prescription for policymakers as to how to transition from one level to the other within the framework that government has used for staging the release of the lockdown. So the basis for this work is looking at the data globally. We have a dashboard, an analytics dashboard that looks into the data every single day, calculates epidemiological parameters. And we've chosen about 100 countries and all the states of the US that have managed to generate a certain control or strong control of the epidemic via non-pharmaceutical interventions. And then we have validated our model, our mathematics, so as to accommodate those complex changes. Of course, the parameters are different for each country, but the mathematics is universal. All right, so that leads us to what we refer to as the dual SRD model. That's documented here on the left. People can download it and we can get feedback from people. This graph here illustrates what the dual SRD model is. So after a lot of thinking and working with data, we arrive at the conclusion that if we want to minimize the number of parameters to have predictability, but want to describe the dynamics of the system, we have to divide it into two. One is what we call latent dynamics, meaning all those individuals that get infected but don't feel it, they are asymptomatic but can pass the virus to other people and then recover, leading to what people refer to as herd immunity. Because those folks are going to pass the virus to other people, we see basically an observed dynamics, which means that the number of cases of people that are going through the healthcare system, and that leads to reported cases. So essentially, we have two systems that are talking to each other and have a slightly different dynamic that we need in order to explain and predict what happens in terms of what we see, where herd immunity is very important. So of course, the model has a number of parameters, but two are the most important ones. One is what we call an stringency index, which is an adaptation from indexing performed by Oxford in the South African context and in the light of the 5-level alert regulatory system that I will talk about in a minute. And it basically quantifies social distancing imposed top-down. Alpha is a parameter that basically speaks to the efficiency of the non-pharmaceutical interventions, and it can be interpreted as how much people adhere to social distancing. And of course, the bigger it is, the better. And this parameter, because of the complexity of the system we deal with, is typically extracted from data. As a result, the model is semi-empirical. And the idea basically was here to look at all the data globally and South Africa, first during the time of pre-intervention, before lockdowns, where the spread was fast, and then observe and quantify and model what happens as the spread slows down. And that also includes South Africa. So I'm not going to go into details here. This is a sophisticated Markov chain using Bayesian implementation of the model, where we are able also to extract, as you see here, the latent infections, or essentially the herd immunity, which I think is an added value of this model. All right, so let's go to predictions for South Africa and the South African context, and that starts with us going through the complex matrix that parameterizes the different 5 levels. Each level is composed of a number of measures that government has issued, and these are classified according to the table that you see here in the bottom right, ranging from school closures all the way to banning of international travel. And going through this complex matrix, you basically end up having what we refer to as the stringency index, which is what you have in the upper right corner, where black corresponds to level 5, and then you go respectively to level 4 through level 1. The different steps, you see the small steps you've got here, that basically has to do with the fact that schools will be reopening gradually, and that is basically quantified by the fraction of students that are going to school. And also we had a very detailed analysis of the fraction of the population, the workforce, that is going to work and is not going to work, and that's also parameterized in there. All right, so these are numbers that the importance of which are not to give you the value of the peak. These are numbers that basically assume 25% of the population having some level of symptoms. This does not speak to the needs for hospitalization. Obviously, the overwhelming majority of people will have mild symptoms that won't require hospitalization. And I will refer to colleagues that have spoken before me as to that question. The important thing here is what is the interplay between the non-pharmaceutical intervention and the social adherence to social distancing, and how that will play out in terms of when the peaks are going to happen and the relative amplitude of them. So what we have here is a graph before we started getting data in May, and I will show data from May, where you see basically that had we stayed on level 5 and with the same level of adherence to social distancing, the peak would have probably have occurred in November. Level 4 would be moving it forward by a month or so, and so on and so forth. Now, this assumes, this is very important, and that has been alluded to by other speakers, that the level of social distancing is coming from before lockdown, which was, of course, very loose. This is obviously a very pessimistic picture. So let's look at the data.
Sorry,
because the importance.
Try and wrap up in the next 3 minutes, please.
Yes, thank you. The importance of a model is not whether it is wrong or right, is whether to compare to the data to understand the dynamic of the data. When you see here in the Gauteng province here, the data seems to be undershooting what would have been level 4 if social distancing had been at the same level as before lockdown. Meaning that it seems evident, or there's a hint from the data, that the population seems to be adhering to social distancing much more seriously than they were before lockdown. As a result of that, we are significantly lower than this dashed line here. Let's focus on the red, which is basically level 4. The impact, in order to bring this level 4 curve to the data, we need to enhance alpha by 20%. So that's roughly the empirical estimate of how much social distancing is adhered to now compared to before lockdown. The importance of social distancing and adherence to social distancing is exemplified here. This is numbers of active cases for Gauteng for different assumptions of small increases of social distancing or adherence to social distancing, where the 20% will basically shift the peak by about a couple of months. That's a very important factor in we want to control the epidemic. Now, let's move on to the practicality of this for policymakers. So based on the mathematical apparatus developed, we're able to arrive at an equation, in particular an inequality that tells us what is the criterion for a province or an administrative unit to go from one level to the other. We need to give a mathematical answer, a quantitative answer. Now, this may sound gibberish to many, but basically the important thing here that can be approximated to is that the relative increase of adherence to social distancing, so the improvement on how well, or how we adhere to social distancing, has to be greater than the change in or the decrease in the stringency of the lockdown. Okay, if that is not the case, then we're basically going to go to very fast increases and not going to be able to control the situation. So in terms of what we showed for Gauteng, the equation for Gauteng looks like the increase of adherence to social distance is about 20%, which is greater than the what's going to happen when we move from level 4 to level 3, which warrants the transition to level 3, and that's the algorithm that we offer to policymakers for different administrative needs. So let me conclude here. So we've developed a dual SRD model that allows us to predict the visible dynamics, the number of cases that the healthcare system sees, but also herd immunity, which is very essential for the future. We've developed a complete stringency index for the South Africa's 5-level alert system, which parameterizes the impact of policies on the spread and social distancing. We are providing, we have a practical recipe for policymakers as to how an administrative unit can move from one level to the other. And we've used Gauteng as a showcase. We're working with clinicians, of course, of the Gauteng Department of Health to showcase the fact that Gauteng, as per today's numbers and as per the last 3 weeks, seems to be ready to go to a lower level, level 3. Thank you.
Thank you very much, Bruce, for that. I think the more details will be in the rest of your slides.